I want to define what is the rank of a linear transformation. The rank of a linear transformation. And here is the definition. It may look weird, at least the first time you see it. Why would you define it as such? But then I'm going to make a remark. So the rank of a linear map T is denoted by R of T, and by definition it's the dimension of the image. That's the rank, the dimension of the image. And we denote it by R of T. Okay. So what I'm going to do now is write a theorem and prove it. And the key thing in that theorem is the following fact. We mentioned several times, and we're starting to get the feeling towards the fact, which we haven't proven yet, that any linear transformation can be presented by a matrix. Okay? We know what the rank of a matrix is, right? It's the number of non-zero rows in an echelon form, or we said that it's the same as the dimension of the row space, right? So we know what a rank of a matrix is. What I'm going to claim now is that if T is presented by a matrix, then the rank of T defined as such coincides with the rank of A, which presents T. Okay? So the two notions, in fact, coincide. Okay? So let's write that. Let's write what we're trying to say. So, theorem. Let A, some m by n matrix, be a matrix over some field F. Define the linear transformation going from Fn to Fm by the matrix T of V equals, take that given matrix and multiply it by V. Okay? V is in the domain space in Fn. It's a vector with n entries, so it's n by 1. So A fits. So this is well defined. A is m by n, V is n by 1. The result is m by 1, which is a vector in Fm. Right? So this is precisely a transformation given by multiplication by a fixed matrix. Okay? So if, this is an if, we're defining T this way. We're not saying yet that any T is given like this. That we're going to say later. But if T is given like this, then we're going to have four statements. Let's call it 0. The first statement we're going to call statement number 0 because we already proved it. T is linear. This we argued before, that something defined like this is a linear transformation. We showed this. This was example 2 in some, I think in the first clip where we discussed linear transformations. Remember that? Okay, so first of all, T is linear. 1, the image of T, as a linear map is related to the matrix A, obviously, because T is given by some matrix. And the way it's related is the image of T is, or equals, call of A. The image is the column space of A. Okay? We're going to see it. It's not too difficult. 2, which is what I referred to before writing this theorem, the rank of T coincides with the rank of A. The rank of A, we know what it means. It's the number of non-zero rows in the echelon form. The rank of T is the dimension of the image. Okay? And 3, which I'm out of space, so I'll write here, and luckily it's short, 3, the kernel of T is none other than the null space of A. Remember what the null space of A is? All the solutions, the space of solutions to the homogeneous system AX equals 0. Remember that? Okay. So let's prove this. I'm not going to prove 0 because we've done it. Okay, if you don't recall, it's very good practice. You need to take V1 and V2, show that T of V1 plus V2 is the same as T of V1 plus T of V2. That's precisely the distributive property of matrix multiplication. Remember we did that, everybody? Okay, good. Okay. Let's show 1. 1 is where most of the work is hidden in this theorem. So I want to show that the image of T is the same as the column space of A. So, proof. 1. Let's take the standard basis for the domain space. So I'm going to take 1, 0, 0, dot, 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 0, and then 0, 1, 0, dot, 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 0, all the way up to 0, 0, 0, 1. This is the standard basis for Fn. Do you agree? So this, let's give them names. Let's call this one E1, E2, all the way up to En. This is a basis, the standard basis of Fn, of the domain space. Do you agree? Maybe we should put these squiggly brackets here. Good? Everybody good? Okay. Therefore, by a theorem we had in the previous clip, if we do T to them, T of E1, T of E2, all the way up to T of En, what do we know about this set? It spans the image, exactly. Do you agree? If you take a spanning set, in particular a basis of the domain, T of it spans the image. We proved that. Okay. But let's understand what is T of E1. What is T of E1? T of E1, we know what T is. T is given by a matrix, a fixed matrix. So T of E1, by definition of what T is, it's A times E1, right? Do you agree? That was the definition of T in this context, in this theorem. So it's A, let's write what A is, A11, all the way up to A1M, and then A21, A2M, all the way to, no, N, right? It's an M by N matrix. And then AM1 all the way up to AMN. This is A. I just wrote what A is explicitly. Gave all the entries names, right? Multiplied by E1. E1 is this. 1, 0, dot, 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 0. Do you agree? What do we get? What is the product of A times E1? It's A11 times 1 plus A12 times 0 plus A13 times 0 plus A14 times 0. Do you see that the first entry is just going to be A11? Everybody else hits a 0 in the multiplication, right? This times this, only A11 hits the 1 and survives. Do you see that? The second entry is this row times this column. Only A21 hits the 1, all the rest get multiplied by 0. Do you see that? And likewise, all the way up to AM1. The last entry is this last row times the column E1, only AM1 meets the 1 multiplicatively and survives, the rest hit 0 and die. Do you agree? So what is that? It's the first column of A. Do you agree? Okay, so this is the first column of A. Do you agree? Okay, and likewise, you can do it for all of these T of EI's, and in general, T of EJ is going to be equal to A times EJ. That's the definition. And that's going to be, if you spell out the details, it's going to be the jth column of A. Okay? If you need to do one or two more, do another one. Do T of E3 and convince yourself that what you get is the third column of A. Okay? So T of this standard basis sends you precisely to the columns of A. And this statement is that the columns of A span the image. Right? These are the columns of A, and these span the image. So the columns of A span the image. The columns of A also span col A, so they're the same. Right? So conclusion, the image of T is the same as the column space of A. Good? Okay. Now let's do property part 2 of the theorem. Let's recall what part 2 said. Part 2 said the rank of T as a transformation, which is just the dimension of the image, equals the rank of A, the matrix which prescribes T, okay, by which T is defined. And that's going to be very easy, but now we are going to rely on theorems that we proved earlier. So R of T, by definition, is the dimension of the image of T. That's how we just defined it. Do you agree? But the image of T is the column space of A. That was part 1. So this is the same as the dimension of the column space of A. Maybe I should put this here. Do you agree? So this is by the definition of the rank of a transformation, and this is by part 1 of the theorem which we just proved. Do you agree? Now we know that the dimension of the column space equals the dimension of the row space. This is a theorem that we proved. I don't even remember if we proved it or not, but this is a theorem that we mentioned earlier. Okay? And the dimension of the row space is R of A. Is the rank of a matrix. We didn't define it as such. We argued that it equals, but in many places it's defined as such. Okay? So again, this is a theorem that we had earlier. So both of these are earlier theorems. Okay? And if you look at the ends of this equality, the rank of T equals the rank of A. A is a matrix, T is a linear map, when T is given by the matrix A. Good? Okay. What about part 3? Part 3 said that the kernel of T is just the null space of A. Okay? The kernel of T is the null space of A. This, in fact, is almost the definition. Almost the definition. What is the kernel of T? The kernel of T is all the guys that T sends to 0. What is the null space of A? It's the solutions to the homogeneous system AX equals 0. Okay? So it's precisely those guys, V, such that AV equals 0. That's what it means to be in the null space. Do you agree? So that's the same thing. AV equals 0, that precisely means that T of V is 0, because T of V is defined to be AV. Does everybody see that? So it's just the definitions. So let's write it. Kernel of T is precisely those elements, those V's in Fn, such that T of V is 0. Right? That's the definition of the kernel. This is the same as those V's such that AV equals 0. Because T of V is AV. That's the transformation we're considering. Right? And this is precisely, by definition, the null space of A. All the V's that solve this homogeneous system of equations where A is the coefficient matrix. Good? Everybody? Okay. So, having said all of this, we're now ready to state the rank nullity theorem for transformations when they're given by matrices. Okay? So we call, so maybe let's write here, this completes the proof of this theorem, right? Okay. So we call, here's the rank nullity theorem that we had, the previous version that we had of it, when all we knew of was systems of equations and matrices. Okay, so let AX equals 0 be a homogeneous system in n unknowns. Then n equals the rank of A plus the dimension of the null space of A. Right? That was the rank nullity system. Rank nullity theorem. Good? Okay. Now let's look at the statement we had so far. If T is given by T of V equals A times V, if T is a linear transformation, not any linear transformation, but one that is given by multiplication by a fixed matrix, then this n is precisely the dimension of V1. I should add that here maybe. If T from V1 to V2 is given by T of V equals AV, then, so n is the dimension, I'm erasing again, sorry. T from Fn to Fm. I want to be precisely in the context of the previous theorem, right? That's the only situation in which I can multiply by a matrix A, right? Okay, good. Sorry, everybody with me? Okay, so if we're in the context of the previous theorem, if we have a linear transformation that's given by multiplication by a fixed matrix, then what is n? N is the dimension of the domain space of Fn, right? Then the dimension of the domain space, let's call it V1. This is V1. Let's take a color. This is V1, and this is V2 in general, right? The dimension of V1 is n. Do you agree? The rank of A is the rank of T. That was part 2 of the previous theorem. The rank of T is just the rank of A. Do you agree? By the previous theorem. The dimension of the null space is the same as the dimension of the kernel, because the null space is the kernel by part 3. So the dimension of the kernel of T equals the dimension of the null space of A, because the kernel and the null space are the same in this situation. Okay? And I want to add one more thing. R of T, by definition, is the dimension of the image of T. That's how we defined R of T. Good? So taking these 3 ingredients together with the rank nullity theorem for A itself, we get the following statements. Statement that the dimension of V1 equals the rank of A, the rank of T, the dimension of the image, plus the dimension of the null space, the dimension of the kernel. So this is the form that the rank nullity theorem takes. And when I write it like this, it's a theorem about dimensions. You don't see any rank, you don't see any nullity, you just see dim, 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 dim. Do you agree? You can almost sing this theorem, right? So the dimension of the domain space equals the dimension of the image plus the dimension of the kernel. We saw it in all the examples that we had, right? We verified it for each example, whether they were geometric examples or examples like this, or examples that were completely unrelated to matrices in any form, right? They all satisfied this, and we just proved it, but only for this case, right? The claim is that this is true in general for any linear map T, not just the linear map T given by multiplication of a matrix. Okay? This line of argument shows this only when T is given by multiplication by a matrix. Do you agree? Okay, so we will prove this. We will prove that this is true. This is valid for any linear map T. But that would be next time. Okay? So is the picture clear? Is what's going on here clear? Okay? So next time I'm going to prove, the first thing I'm going to do is prove this as a standalone theorem without being related to matrices in any way. Okay? And the reason I want to spend time on it is because the proof kind of exhibits ideas that are important. Okay, it's not a very difficult proof, not a very long proof, but I still want to do it. Okay, and then we want to continue to the argument that we still are only hinting at, that this is in fact a general situation. That if you start with a completely abstract T from V1 to V2, you can somehow generate a matrix A such that T can be written in this form for that matrix A. Okay, it still may look a bit mysterious, but we have some clues as to how it goes already. Okay, but we'll get there. Any questions about all this? Okay, you may need to read it again and connect the dots. Kind of, there's a lot of words here that if they confuse you, you need to just think of the definitions and read everything we did in this current lesson again. Okay, what is the kernel? What is the null space? What is the rank of T, the image, and why these 3 statements are true, and that gives this for free in this case. Good? Okay.